All right. Chapter 11, which is our second to last chapter of the trimester, is starts out with a section called Permutations and Combinations. Our EQ is how can I use the fundamental principle of counting, which is actually backwards. It should be fundamental counting principle, to quickly count possibilities. So what we're going to do today is learn how to, like if the question arises, how many ways can blank occur, then you can count those possibilities quickly without having to like write out all the possibilities. And the warm-up's a great example of that. Let's say you get one sandwich, one side, and one dessert for lunch. How many different lunches could you order? So under sandwiches, you have 4 options. It's hamburger, cheeseburger, veggie burger, or PB&J. Side has 3 options, and dessert has 4 as well. So one possible lunch that you could ask for is a hamburger with potatoes and apple crisp. I could also go hamburger, potatoes, and banana. Maybe I want a hamburger, potatoes, and flan. Maybe instead hamburger, potatoes, and rice pudding. Or maybe I don't want potatoes and instead I say beans and apple crisp. You get the idea. There's a lot, and I don't want to list them all out. So one way to do this is to think, okay, I've got 4 options for my burger, or sorry, 4 options for my sandwich. So if I choose a sandwich, each of those sandwiches can go to one of 3 different sides, and each of those sides can go to one of 4 different desserts. So how we could quickly count the number of possible lunches would be to take the number of sandwiches. Each one of those sandwiches has 3 possible sides, and each one of those sides has 4 possible desserts. So I can just take those options, the number of options for each category, multiply them together, and that will give me 48. Now, I'm not going to waste the time to go through and list all 48, but there are 48 different lunch options available. So what we've just done is used what's called the fundamental counting principle, to, instead of listing all the possibilities out, to just like do some quick math and figure out it's 48 ways or 48 different lunches that we could put together. Okay. Again, FCP is how it's abbreviated, allows us to count possibilities using multiplication. Okay. So an example of this would, let's say I have 10 dress shirts, 6 pairs of dress pants, and 2 pairs of shoes. Assuming I'm not trying to like match, I'm just putting together an outfit. How many different outfits could I have? And again, I'm working with 3 different categories, right? I have a shirt. I have a choice to make about which pair of pants I wear, and I have a choice about which pair of shoes. Okay. Since I'm dealing with 3 categories, I'm going to end up multiplying 3 numbers together. And in each blank, I'm just going to put, or in what we call them slots, in each slot, I'm going to put how many options do I have for that decision. So when it comes to the shirt decision, I have 10 shirts to pick from, and I got to choose one of them. Pair of pants, I've got 6 options there. And finally, the shoes, I've got 2 options there. So I'm just going to multiply 10, 6, and 2 together to come up with 120 different outfits that I could wear. Now, obviously, as the number of categories or the number of choices increases, these numbers will grow very quickly. So in this particular instance, I have 120 different outfits I could wear. Another place where this shows up, which is kind of interesting, is license plates. So in Minnesota, a standard license plate is 3 numbers followed by 3 letters. There's no restrictions on the numbers, so it could be any number from 0 up to 9. And we've got 3 of those followed by 3 letters, again, A down to Z. So like I've got 6 total slots to fill on this license plate. The first slot is a digit from 0 to 9. And what might be tricky, like that's 10 possibilities, because if you count 1 to 9, but then you have to include 0. So there are 10 possibilities for the first number. You can repeat numbers. It doesn't say anything about you can't repeat numbers. So this would be 10 for the second, again 0 to 9, 10 for the third slot. But then after we get to the second half of the license plate, which is a letter, there would be 26 for the A through Z, 26 again, and 26 for that third slot. So now I'm going to take those 6 values and multiply those together. 10 times 10 times 10, 26, 26, 26. So I'm just going to use powers for this. I'm going to do 10 raised to the third times 26 raised to the third. Whoops, not what I wanted. 10 raised to the third, get out of the power, times 26 raised to the third. Gives me, what's that, 17,576,000 different license plates, which is a lot because we only have about 9 million people in Minnesota. So there's obviously way less than 17 million cars, so we're good there. And that's just a standard license plate. In Minnesota, there are some other license plate options as well. You can get a specialized license plate or a specialty license plate. That's a little bit more expensive, but that money goes to like preserving wildlife or preserving natural resources. And so those specialized plates only have 2 letters followed by 3 numbers. So this is a letter, and then number. There are 6 characters. You'll see like here's a 2 and there's a 5, but that number is fixed based on what license plate you want. So if you want the one with the loon, that first digit will always be 2. And so there's only 5 slots to fill. So I have 26, 26, 10, 10, and 10, which obviously now that I have 1 fewer possible space to fill, it's going to lead to fewer possibilities. So of this specific license plate, there are only 776,000 possible ways to have that license plate. Okay. So 17.5 million of the standard, and then 676,000 for those specialties. And now the follow-up, or the interesting next question, is what if we take the standard plate on the left, but you can't use the same number or letter twice, so you can't repeat anything. So it's kind of interesting how that changes. We still have 6 slots to fill, and the first one's a number, so there's going to be 10 possibilities. Next one's a number, but I can't use the number I just used. So let's say the first number is a 6. Now I have 0 to 9, but I can't use 6 again. So then this will go down to 9 possibilities. And now there are 2 numbers off the board, so the third number only has 8 possibilities. And you can see how that would keep going down by 1 if we had more digits. But now we switch to letters, so there's 26. I've used that letter now. Whoops. So it's not 26. The next letter is 25. And the next letter is going to be 24. Okay. So if I do 10 times 9, this is the downside. Now I can't use powers. 26 times 25 times 24. That is decreased to 11,232,000. Okay. So we went from, if you took out repeats, I lost about a little over 6 million possible license plates that had some sort of repeat character in it somewhere. So went from 17.5 million to just over 11 million. So that's how this fundamental counting principle can show up in license plates. You would never, ever, ever go 111 AAA, 111 AAB, and just like list all the possibilities. There's 17.5 million of them. It's a waste of time. So if you want to pause this in just a second, after I explain. So let's say I have the following requirements for one of my passwords. I need 8 characters total, so 8 symbols, letters, numbers, whatever. It needs to have 1 number. and it needs to have a special character. This is a pretty standard, like for a couple of my passwords, like this is what it requires. You need 8 characters. You at least need one number, so it can't just all be letters. And you need some sort of special character, like an exclamation point or a hashtag or $, etc. So let's say I have a password that's 8 characters long. Okay, so 8 total. The first 6 are letters, and then I have a number, and then finally a special character. How many possible passwords could that be? How many different passwords fit that description? Since I know it's 8 characters long, I'm going to put 8 slots on here. 1, 2, 3, 4, 5, 6, 7, 8. Now, the first 6 are letters. Now, here's what's tricky is back in the license plates example, we only had uppercase letters, like all letters on license plates are uppercase. But for a password, you could have either upper or lowercase, right? A capital A is different than a lowercase a. So for this first letter, there are actually 52 possibilities, not 26. 26 letters, but then each one has an upper and a lowercase, so we have 52. Nothing about this password says I can't use the same letter twice in a row. So every single one of these first 6 letters is going to have 52 options. 52, 52, 52, 52, 52, or 52 to the 6th power. Then I followed that with a number. So 0 to 9, I have 10 options there. And then I have some sort of special character. And if you count the special characters that are listed, there's 1, 2, 3, 4, 5, 6, 7 different options for those. So there are 7 possibilities for that last slot in the password. I'm going to go ahead and 10 times 7 at the end here is 70. So I'm just going to do 70 times, it's multiplication, so the order doesn't matter. 70 times 52 to the 6th power. And that is, oh boy. So E12 means that I would have to list 12, move it over 12 decimals. It's a lot. 1.3839. So let's see, 1.3839. But I move this over 12 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I fill all these in with zeros. You can see why there's a lot of different passwords here. So that is 1, 2, 3, 4. Millions, billions, trillions. So based on this, I have 1.383 trillion different passwords. And what's crazy about that is telling, like, that is if you know that it's 6 letters, 1 number, and then 1 special character. The fact that I could throw a special character in the middle, or I could do number, letter, alternating, like, this gets out of hand very quickly. But if I wanted to calculate the number of possibilities for this one specific situation, that's how I would do it. So that is a ton of possible passwords, which is why if you get hacked, it's not great, but there are people out there trying probably right now to figure out what your password is. Okay, so let's say, again, this is probability, so almost all of these are going to be word problems. Miss Whistler owns the entire 8-film collection of Harry Potter. There's 8 films, 7 books. How many different ways could she arrange the movies on her shelf? So if you think, like, she's got all 8 movies, she wants to put them on the shelf. Obviously, like, if she just puts them in order, 3, 4, 5, 6, 7, 8, that's one arrangement. But let's say she takes the last 2 movies and swaps them in a different order. When we're talking about arrangements, these 2 are different. It's a very specific order arrangement, meaning it physically looks different, and these 2 would look different. Obviously, like 8 movies, there's a lot of different spots for these 8 movies. This is going to be a pretty big number. Now, I'm going to lay this out using the 8 slots to fill out 5, 6, 7, 8. So let's say she's holding all 8 movies in her hand. She has to choose which one goes first. Okay. Well, for which movie goes first, she has 8 options because she's holding all 8 movies. But now she has, like, she's placed 1 movie. She's got 7 movies remaining in her hands. So how many options for the second movie on the shelf? There's 7. For the third movie on the shelf, there's 6. So on and so forth. This goes all the way down. 5, 4, 3, 2, 1. Now, on the calculator, that is annoying to do. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you already know the trick to multiply this, you're probably yelling at the computer right now. So there are 40,320 different arrangements that she could, 40,320 arrangements of the movies on that shelf that she could do. So lots of different possibilities. Mrs. Lucan, you're going to have to wait. Hold on just a second. I'm making a video. Can I call you in a minute?
Oh, yeah. I'm just on my way. I'll just pick you guys up.
Bo already left.
Okay. All right. Bye.
Bye. Mrs. Lucan, everybody. All right. So 40,320 arrangements. If you are multiplying every number down to 1 in order, so like there we did 8, 7, 6, 5, 4, 3, 2, 1. That's what's called a factorial. And a factorial in math means that, again, kind of what we just said, you are multiplying all numbers from some number n down to 1. Okay. So for instance, 8 times 7 times 6 times 5, that calculation we just did could be written shorter as 8 factorial. And we use the exclamation point in math to mean a factorial. So that's another way to write it. And that's actually something that's accessible on your calculator. So if you first type the number 8 and then go to the math menu, we're going to be using this probability tab a lot. So if we go over to probability, I see that the exclamation point down on 4. So 8 factorial, and that gives me that 40,320 right away. So if you think about, if we did this with the Harry Potter books, okay, if you think about the books, there's only 7 books. So instead of doing that whole calculation, I could just do 7 math prob 4. So there would be 5,000 different arrangements of just the books, 40,000 arrangements of the movies because there's another movie. Whoops, not that one. So if you see that multiplication symbol, that means you're going to multiply every number from that down to 1. Last thing we're going to talk about is a permutation. So a permutation is, hold on, this is going to load quick. A permutation is an arrangement of things in order. We actually just did the example that we talked about with, the example we just talked about with arranging the movies or books on a shelf. That's an example of a permutation. So you're arranging things in a very particular order. So an example of a permutation would be how many 4-digit numbers can be made if I'm only using the digits 1, 2, 3, 7, 8, 9. So I'm going to make a 4-digit number. Each number, since I'm only working with 1, 2, 3, 7, 8, and 9, I have 6 possibilities. And it doesn't say anything about not repeating myself, so I'm just going to multiply 6 4 times in a row. Okay. So if I wanted to make a 4-digit number with those, I would do 6 to the 4th power, and that'd give me 1,296. Okay. And then what if I can only use each number once? So again, this would be 6, but then we go down to 5 because I can't use the first digit again, times 4 times 3. So this would be 6 times 4, 6 times 5 times 4 times 3. And that's 360 different ways. So that cuts down on the number of, that cuts down pretty drastically if I say you can't repeat a number. We go from almost 1,300 possibilities to less than 400. And now this is where it gets interesting, and it's going to take a little bit of practice with these last two problems. How many odd 3-digit numbers can be made with no repeats? How many odd 3-digit numbers can be made with no repeats? The fact that a number has to be odd means you look at just the last digit, right? So an odd number has to be 1, 3, 5, 7, or 9. It has to end with one of those. But I can't choose any of those 5 numbers because the only odd ones I'm working with are 1, 3, 7, and 9. So that means that I have to choose the last decimal first. Sorry, not decimal. I have to choose the last digit first. 1, 3, 5, 7, and 9. So I have 4 possibilities because 5 was not one of my options. Okay. From there, the rest of the numbers are free. So here's what is tricky. I can't use a number again, okay? But I've picked one of the odd digits to put at the end, which means now if I go back to the front number, it can be anything. So this is actually 5 possibilities, not 3. I only had 4 options for that last digit, but now it's open to the whole pool of numbers. So this goes 5, and then since I've used 2 numbers so far, I'm down to 4 for that last option. So 5 times 4 times 4 means there are 80 different numbers that I could make. We'll talk about this one in class as well because this is one that can be a little tricky. Same sort of thing here. How many 3-digit numbers greater than 500 can be made? So a 3-digit number that's greater than 500. Notice it doesn't say anything about no repeats. Okay. So as long as the front number is 5 or higher, then it's fair game. Everything's a possibility. So we have a 3-digit number. It has to be greater than 500, which means of the numbers that I have, this has to be 7, 8, or 9. So I have 3 possibilities for that first digit. After that, as long as it's 7, 8, or 9, we know it's going to be over 500. So these last 2 slots each have 6 possibilities. So I got 3 times 6 times 6. 36 times 3 is 108. So there's 108 possibilities, or 108 numbers there. Okay. So that's how we can kind of use the same idea, that counting principle, but now we are looking at very specific situations. Finally, we're going to do 8 runners are competing in the 400-meter dash. The top 3 get medals. How many different arrangements are there of the top 3 finishers? So if you think like, let's say the runners in lanes 1, 2, and 3 are the top 3. That's great, but the order does matter because like 1, 2, and 3 is different than 3, 1, and 2, right? In this case, gold goes to first place, silver goes to second place, and bronze goes to third. So we have 3 medals to hand out. 1, 2, 3 medals to hand out. For who gets gold, there are 8 possibilities, right? Everybody's running the race. Race isn't over. First one across the line gets gold. Silver then has 7 possibilities because someone has already gotten gold. And then bronze, we have 6 possibilities. So if I multiply all of those together, 8 times 7 times 6, that is 56 times 6, 8 times 7, I think 336. 336 possible. How many different arrangements are there of the top 3 finishers? 336 arrangements. So we have another day on 11.1 to talk about something called combinations tomorrow. But this is kind of how we use that fundamental counting principle to count the options that we have very quickly. So the homework is worksheet 11.0, which you can find on Schoology.